First of all, when we think of charges, charges can exert force, repulsions and attractions. And I think most of us, maybe with the exception of the people here in this audience, don't really think of charges as having really powerful forces. We think, we touch something, we get a shock, and okay, but we don't think of really strong forces. So the first question is, well, how strong are charge forces? If you got a plus and a plus near one another, is it weak? Is it strong? Next question. Where on the earth do charges hang out? Okay, and I want to talk about the earth itself and the atmosphere and the charges that we find there. And the next question, which you could have surmised, is, are there really gradients of charge that we can identify? And then can charge gradients really drive the prevailing winds? And if so, can the prevailing winds spin the earth? Okay, so first question, how powerful are charge forces? Well, one of the phenomena that got me started is something shown by our previous speaker, Don Scott, in one of his books, and that is, if you put a proton next to an electron, let's say at a distance d between them, there are actually two forces that you can think of. The first one is the obvious one, which is the attraction, the electrostatic force. But also, since the two have mass, there's a gravitational force. And the question is, okay, which one is stronger and by how much? And I'm sure most of you will of course, guess that the electrostatic force is larger than the gravitational force, but by how much? See, so that's a question. And the answer turns out to be 10 to the 38th. It's not trivial. It's a huge amount. But I think most of us don't really understand what 10 to the 38th really means. We can understand 10 times or 100 times or 1,000,000 times, but 10 to the 38th. 10 to the 38th is something like the schematic shown here. If you take a proton on the upper left and consider the diameter of the proton, okay, and then consider another distance. If you look at next to the last panel there, you see the solar system. And if you take the distance from the sun to the edge of the solar system, take the ratio of that distance to the diameter of a proton, that's only a mere 10 to the 19th. We need 10 to the 38th. So we're talking about the ratio of the size of a proton to the distance between us and some distant galaxy. That's 10 to the 38th. It gives you some idea about how strong the forces are, the electrostatic forces compared to gravitational forces. Okay, here's another example. You take two copper balls sitting on top of one another, and you start removing electrons from each one of them. That, of course, leaves the two copper balls positively charged. And so the question is, well, how many electrons do you need to remove so that the top one levitates? Okay, and I don't know, maybe you know the answer to that. It turns out the answer is 1 in 10 to the 7th. In other words, only 1 in 10 million, approximately, electrons need to be removed so that this ball, because of repulsion, starts levitating, a really small force. Another example, you take a light bulb, take one of the old-fashioned 120-watt light bulbs, and you know the current goes through the filament, right? And if you could, suppose you could capture electrons, and capture, let's say, 1 second's worth of electrons running through that filament. And suppose you could take that and compress it into, just like a sort of a nucleus of positive charges, you compress it into a dot. And you put one of those dots down at the bottom, resting on the ground, and the other one 1 meter higher. And so the question is, in order to prevent the levitation, and to keep it where it is, how much weight would you have to put on that? Anybody want to take a guess? Lots. Okay, thank you. Okay, the answer The answer is 50,000 fully loaded garbage trucks. I would have shown jumbo jets, actually, there are 5,000 fully loaded 747s, but my son, the artist, couldn't draw them. Okay, and here's finally, not to belabor the point, but it's an important point. Consider this. Suppose you're lying down and somebody is lying or suspended, let's say 1 meter above you, okay? And you remove 1% of her, she's got a lot of electrons and protons, you remove 1% of her electrons and 1% of the electrons of the person below. They're 1 meter apart. And of course, both of them become positively charged, so instead of coming together, which they might like, they're actually coming apart. And the same question, how much weight would you need to put on top of the upper person in order to prevent the levitation? I guess? Lots. Okay, how much is lots? Right, the Earth. the weight of the Earth. And this is not my calculation. You'll see it in Feynman's lectures. He calculated it. I guess he knows how to calculate. So in other words, the point of these somewhat repetitious slides is that charge forces can be astonishing. And if we don't take into account the force exerted by those charges, we're missing something, and probably we're missing something really important.